Thank you, Chairman. Thank you, organizers. Okay, so this is about, oops. Yeah, this is about an experimental work. The experiments were carried on in Dom Truzzolillo's group in Montpellier in France. And Alessandro was the primary person who carried out the experiments. So this saga has been going from 2017, as you can see. Like this summarizes everything. So initially they started out looking for some instabilities that we had predicted a very long time ago in our group. So like we had this theory and they were doing the experiment trying to predict that instability. So they first got in touch with us in 2017. And since then, I've been barking up many different trees, like doing lots and lots of wrong calculations and never understanding it till last year. And last year, we started getting, I mean, we had some correct results from before, but we could get a much clearer picture of what's going on. So that all of that is in this paper. So the story is about surface tension in a miscible fluid pair. When there's immiscible fluids, we all know about surface tension, right? It's like high school stuff. So in high school stuff, you have oil and water, which you're told will not mix with each other. And so water, actually I've exaggerated the size of the water molecule. It's way, 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 way smaller than the oil molecule. So you can imagine like it's really small. And now what happens in water is that the hydrogen bonding between, neighboring molecules, that oxygen and this hydrogen takes place. Although it's a weak force compared to some other forces, it's way, way stronger than things inside the oil. Inside the oil, there is van der Waals forces of various kinds, like London dispersion kind of thing. And so they stick to each other because they have some attractions. These guys stick to each other because they have stronger attractions. And here is an interface. So I've kind of drawn water and oil. I think the oil is even bigger, the molecules. So then there is this interface and everybody likes to keep the interface flat and, stay on either side of the interface. So this is like an immiscible system. So like now what happens is you get capillary waves in the interface. So technically the interface, no molecule likes to be on the interface. So it keeps pulling inwards, right? The oil guys and these guys. So they try to reduce the surface area of the interface. So you will get straight lines if you look from the side. So like the interface likes to be a straight line. That's the basic moral. Here I've drawn the oils much smaller, but they're bigger. Now we can actually, this interface which is totally flat can support neutral waves. It can support wave-like solutions, and those are easy to see. Those were known like, 130 years ago and even more. Like Lamb is a textbook. He didn't invent all of this. So like it was known. So what happens is you can pretend that this flow doesn't have viscosity and doesn't have vorticity. So you call it potential flow. You can write a potential, expression which satisfies the inviscid, the Euler equations. And then you can write an expression for the interface in a wave form. K is the wave number and omega is the frequency. So everywhere K will be the wave number and omega will be the frequency. So this is the shape of the interface eta, and we're looking at individual sinusoidal waves where X is this direction. And all of you know this expression, right? Like the pressure difference between there and there will be proportional to the curvature, and the constant multiplying it will be the surface tension. So this is depending on how much is the hatred of one thing for the other, you will have a pressure drop across the interface, right? So then like this beautiful expression comes out. Omega square goes as K cube with a proportionality constant of surface tension. So like the frequency to wave number, there's a nice 3/2 law, which, gets satisfied. And now we see that any K that I put in, I'll get a omega. So which K am I going to see in the experiment? That's a question which we don't have a complete answer, but I will leave it open. We can talk about it at lunchtime. Now, if there's a water molecule which goes there in an immiscible surface, we know that it will hate it and it will get pushed out because of the attractions and repulsions we talked about. What happens when this thing is fully miscible? So suppose I have water here and something which mixes with water above it. Now there's no hatred of one for the other. So what happens? So like, but my title is surface tension when it's fully miscible. So like the basic finding we have in this work is that you can actually have capillary waves, surface tension waves, when you have like water and glycerol, for example. And it could be a bunch of other things. We've done the experiment with glycerol. Glycerol is a much bigger molecule than water, but you see all these OH groups. So you have hydrogen bonds between glycerol and water, but it's not ideal. Like if a water if like here are all the glycerol molecules, they're also much bigger, as you can see, than water, but they're very miscible. So like if I wait long enough, I'll get an average concentration of reds, blues and greens everywhere, and then there'll be no surface tension. There's no interface. It'll all mix completely. But at short times, when I just put water and glycerol here, now if a water molecule goes there, it has a chance of hydrogen bonding right there. So it need not come back with that alacrity. At the same time, they will have like some preference for their own kind and less preference for the other kind. So that reluctance to mix is kind of giving something like an effective surface tension, which is giving effective capillary waves. Okay, so this thing is again not new, okay? In 1871, this guy Boscha, or however you pronounce it, he put some, let's say salt water in plain water, something like that. And he saw that the new thing that he's putting, although it mixes perfectly with the fluid, is adopting a spherical shape. Spherical shape it does only if it's got surface tension and wants to reduce its area, right? So when these molecules like each other, like why are they, pretending that they don't like each other? And this is a much later experiment of 1990 of oil in oil, which again sees the same, like as it rises, like this is soon after release and this is a long time after release. It's like trying its best to be spherical. So the Korteweg had wondered about Boscha's experiments, and he also modeled stresses between a liquid and its vapor. I think lots of people know about Korteweg stresses. And he showed that it behaves like a surface tension. So when there are, liquid and vapor, there's a density jump. So he had modeled everything according to density jumps, and you can write like a surface interface tension in, expansions in powers of grad rho, and you can get various answers. So if you stop at the quadratic, there are various kinds of quadratics you can get. If you stop at that, you get like this square gradient model, which is quite famous. What did we do? So we had a little micro channel. This W is 1 millimeter, okay? And the other side is even smaller. So where we pumped glycerol and water, we means they did it in France. So we pump glycerol and water at different rates, and then we see what happens. And we saw that glycerol and water love each other. They can hydrogen bond, this and that. Now what happens is that between the glycerol and the water, there's a small layer, thin layer, which grows where everything is mixed. There's glycerol molecules and water molecules. That thickness is delta. And knowing diffusion, the diffusion rate is very small. I can write something like this. And if I, measure at a distance x, I can replace time. So these things are flowing at a certain rate. So I can put a window at a certain place in the experiment and measure like what happens to the wave. Like basically ask if waves can form and what happens. Of course, like the diffusivity is a very strong function of the concentration. So it isn't very simple to do anything here, but you can actually get some evidence of surface tension. And as this delta becomes very thick, you will not have any surface tension. So 2 minutes. Surface tension is a phenomenon which happens only very close to the leading edge. Okay, so these are the profiles, and this is what we saw through the microscope window. And you can see pretty clean waves because of the refractive index change. So, of course, we spent a lot of time looking for this old instability of ours, where like, the behavior has to be omega is proportional to k if you know C. Whereas here it was a 3/2 law, as you saw. So it took us a long time, like, we tried various variations of this theory, but it took us a long time to know how to scale it. When we finally learned how to scale it, you see capillary waves all lining up in the 2/3 law, and the inertial waves all lining up in the omega equal to k, omega by c, whatever. It's scaled properly, so it looks like that. And then a few points which looked like neither. So this is the kind of thing. And whenever things are flowing very fast, we are able to capture surface tension. So at fast flow rates we get, and none of these waves comes when it's very slow because it's an instability. Okay, so this is the final answer. We can actually measure surface tension as a function of time, which is effectively like measuring surface tension as a function of the thickness of that interface in microns. And you can see like a sharp decline by, much less than 1 second. So you actually have a surface tension. You see that it doesn't obey the Korteweg stress thing. So something very nonlinear, very different, and very sharp is going on here. And this needs a complete theory. So capillary waves are seen in completely miscible fluid pair. And this thing which we found must have some application. And here is a nice experiment where we can actually measure everything. That's the beauty. We can actually measure surface tension at very, very short times with pretty good accuracy. And because we know this, we know the answer. Thanks for your attention.
Thank you, Rama. Questions?
A small question. So you are working with the fluids which have different densities. Can this thing also happen in fluids with same density?
They actually don't have very different density. Because in water and glycerol, they've added something to water to make the density matched. So they tried their best to match the density. So these things are very different in viscosity, which is why we were looking for viscosity-based instabilities, but density is reasonably matched.
Just to clarify.
Wait, the Korteweg had modeled it according to density, but it can be done in concentration. You can have an equivalent one in concentration. Yeah.
I'm slightly confused between the two fluids. What all the things is different? So,
Water and glycerol.
I don't know, but so density is same. Viscosity difference has been accounted for, and surface tension difference is also there.
Actually, there's no surface tension because they're fully miscible. So at long times, there's no surface tension. You can put 1 spoon of water, 1 spoon of glycerol and mix.
Right. And the flow rates between the two pipes, are they the same or is this?
So we have a huge range of this one and that one to get all those experimental points. So we have a huge range of calculations of eigenvalues and everything as well as this thing.
So even when the flow rates of the both channels are same, then Kelvin-Helmholtz, if I think of it loosely, that will less likely get triggered, right?
Because this is very viscous, very low Reynolds number.
I see.
No Kelvin.
Yeah, 1 millimeter. Yeah, okay.
Slightly question related to what Neha asked. So is there a necessity for a molecular level of change between the two liquids? For example, in the ocean, I can have 2 layers of liquids having similar density, but very different temperature and salinity. So will I see something like this there, or do we need a molecular level difference in the fluids for this to happen?
Actually, like because, that old 1871 experiment saw it between 2 aqueous solutions. I think salt 1 and salt 2 or something. So in principle, you will see it, but it will be so short-lived. So like the applications are in micro channels or something like that. In the ocean, it will go away in much, much less than a second.
Because of the Reynolds number being larger?
Because of the Reynolds number and because of the diffusivities, the length scales are so big.
Okay.
So like before it's gone even a slight distance, it will diffuse more than a micron or whatever this is.
Thank you.